Okay, hello again, and we're going to be talking here about some basic concepts of digital recording, and of course this is what we've been doing all along, but we will get into some of the particulars here a bit more so and focus on the digital aspect of the recording. The theory of digital recording goes back as far as the 1920s, and the young man you see there on the right was named Harry Nyquist and developed what is called the Nyquist theorem. And we're going to see a video about this, or at least it'll touch on the Nyquist theorem here in a moment. But this is based on binary math. And I remember first hearing about and learning about binary math in sixth grade, and it made my head hurt then and still does. This is where all numerical values are expressed with 0 and 1, only those two digits, and really all computer operations, all computer systems are based on binary math. Binary math first came along in the 1700s, so all of this has a fairly long history. But let's look at something here on digital audio sampling and the Nyquist theorem.
Hey, what's up? It's Wick for Wikimedia, and today I'm going to talk about digital audio. So I'm going to talk about the sample rate and bit depth. The act of capturing an amplitude value is called sampling. A sample is actually a static representation of a waveform in time. The amount of samples that are taken per second is what's called the sample rate. If we sample a 20 kHz frequency with a sample rate of 20 kHz, we only have one sample per completed cycle. To capture the positive and negative side of the cycle, we'll need to have a sampling rate that is double the frequency that we're sampling. In other words, to capture a 20 kHz frequency, we'll need to have a sample rate of at least 40 kHz. This is the basics of the Nyquist theory by Harry Nyquist. The highest frequencies that we're sampling can cause some aliasing errors and other problems, and thus these can't be properly captured. We'll need to filter off the highest frequencies that we're sampling with a low-pass filter, and this is the reason we'll need to get a higher sampling rate than 40 kHz to properly capture a 20 kHz frequency. Keeping in mind that then the cutoff frequency of the filter is around 20 kHz, so we don't lose too much of the original signal. So we can say that sampling is capturing an amplitude value in time. This value is captured in a process called quantization. As well as with the time axis, digital systems have a certain resolution on the amplitude axis. The higher this resolution is, the more accurate the digital representation of the waveform's amplitudes. This is determined by the bit depth of the recording. The higher the bit depth, the more dynamic range can be captured. So a 24-bit system has a higher resolution than a 16-bit system. A 16-bit recording has a theoretical dynamic range of 96 dB, whereas 24 bits audio has a theoretical dynamic range of 144 dB. You can imagine that mixing with audio that has a 24-bit resolution is much easier and more pleasant to mix with compared to 16-bit, since we literally have more values on the amplitude axis. So why a 44.1 kHz sample rate? This sample rate standard dates back to the days of video cassettes. It was chosen because it was higher than 40 kHz, and that was needed to replicate the 20 kHz audio, and it was mathematically compatible with both the European PAL as the United States NTSC standards for film. The 44.1 kHz sample rate with a 16-bit bit depth was also adopted as the audio quality for the standard audio CD. So this sample rate has been relevant for years, and it actually still is. Common sample rates that are used nowadays can be a bit higher. Not only does this mean that we can theoretically record higher frequencies, but it also means that we've got a lot more samples that are taken to represent our audio.
I'm going to pause that at that point. He goes on for a bit longer, quite a bit longer, and you can watch that entire video if you want to. Of course, this outline is available for you on my Leo 2DL, but that covers most of what we're interested in, and some of that we have talked about before, but not specifically in this context, and so I think it's good to come back to that again. But the sampling rate, the bit depth, and all of that, very relevant to us in the work that we do and the production of audio that we do. So recording in the digital domain, of course, when you are producing a project, we've talked a little bit about this, haven't talked as much about it as really we should. You need to rely on meters to judge the amplitude or the volume of the recording that you are creating. And there are meters on the board, and there are meters within Adobe Audition as you are recording. We're not really working with the traditional VU meter, which you see down here in the lower right these days, but we work with LED and peak meters both within Adobe Audition. You see that meter at the bottom of the screen, which you should pay close attention to. And then you see on the board where you are doing your original recording and producing, especially recording your voice, then you see an LED meter there that you should pay close attention to. So let's look at this video now on types of audio meters.
Welcome to this tutorial on audio metering. Audio meters are essential tools for project and home studio owners. They provide a visual means to monitor signal levels during recording and mixing. There are many types of audio meter, but the 5 primary types are single LEDs, peak program meters, VU meters, phase and correlation meters, and loudness meters. All of these types of meters can be used to either show signal level or the amount of gain reduction being applied by a compressor or limiter. Single LED meters change color and intensity according to signal level. They usually show green when a signal is present and red when the signal is within the headroom of the device or clipping. Some LEDs change intensity, glowing brighter to indicate louder signals. Single LEDs are sometimes used when cost factors prohibit the use of peak program meters or VU meters. Peak program level meters or PPM meters display the peak level of signals in audio equipment. There are many types of PPM, and they all help the studio engineer to determine the peak levels in a sound wave signal. One type of PPM is the true peak program meter.
And this is, although again, there's a lot of different styles and they have different aspects to them, but this is basically the type of meter that you see on the board, that we have the Audio Arts boards that we have in our production studios, and basically it's quite similar to the meter that you see on Adobe Audition at the bottom of Adobe Audition, although that's not an LED meter, but it is what's called a peak meter,
which displays the changing peak level of a sound wave signal. They are used to identify the loudest peak in a signal. Another type are sample peak program meters, also sometimes referred to as digital meters, which display changing peak sample values. These types of meters are used in digital mixers, effects processors, and DAWs. Good practice dictates that when using these types of meters, 3 decibels of headroom should be allowed to accommodate inter-sample peaks and avoid distortion. A peak level of -3 decibels is therefore required. Peak program meters often have a separate indicator which turns red whenever the signal level exceeds that which can be accommodated by the word length of the system. This indicates that digital clipping or distortion has taken place and the level should be reduced. The VU meter was developed in 1939 to display signal level in audio equipment. Due to the ballistics of its meter, it is unable to show peak levels or spikes in volume. It is therefore not good at showing peak levels. Interestingly, this limitation makes it better at showing average level, which is loudness, and this explains why it has remained popular. However, the VU meter cannot tell us what a recording's average loudness is over its duration.
I'm going to pause that there. We're not using VU meters, traditional VU meters, all that often now, so we'll leave it at that. But Adobe Audition uses a peak meter. The Audio Arts console meter is an LED meter. It really measures in VU scale, but it's an LED meter. It's not a traditional VU meter. It shows that 3 dB headroom area to the far right that he was referring to. Basically, in recording of audio, of course, obviously you're trying to capture accurate sound. What I was going to say, and I may come back to this, I'm not sure if this is in the outline, but what I was going to sort of ad lib was that basically with our recording, you want to stay out of the red. And that has changed since the days of primarily using the VU meter, where you could get into the red, you just didn't want to stay in the red. But with digital recording, basically, you want to stay out of the red. You might touch in there just, for a brief moment, less than a second, and not really suffer any noticeable distortion, but you certainly don't want to stay there for very long. If you record, if your recording is too low, then you're going to pick up some background noise, and you'll hear some hiss, possibly just kind of coming from the electronics, the ambiance of the system. So you don't want to be too low. If you are too high, on the other hand, you have the hard clipping, which just actually knocks out the audio for a moment. And before that, you'll notice distortion, which will make the sound unpleasant and harsh and not natural sounding. And again, so there's the admonishment to stay out of the red in digital recording. Now, a rule of thumb, and this is a little surprising, even for me, and we don't do a lot of this now, but a rule of thumb for doing digital audio on a VU meter, and this is a traditional VU meter like that, you would want to stay at about negative 10 dB, which doesn't show to be very much audio, but that is recommended, maybe a negative 15. And again, this has to do with staying out of the red, which is something that we used to not worry as much about when we were doing analog audio and using VU meters. You could get into the red, but just don't stay in the red. But with digital, we don't want to do that. And also, this is about allowing for the headroom that he was talking about in the video. With editing is a remarkable thing in digital audio. I say the most incredible feature of digital recording, the ability to cut and to paste and zoom. I say that because I do remember the days of using audio tape. I started out using audio tape, and even though I'm not going to ask you to do that, that might be a great exercise sometime, but we just probably won't have time. I'm going to show you a little video about editing audio tape, and I mainly show you this just to appreciate, Adobe Audition and other forms of digital audio editing.
I've transferred 2 different takes from my multi-track session to my 2-track machine. I'm going to edit from take 5 to take 6 on the second bar of the re-intro. Put the machine into edit mode so you can hear the audio when you scrub the tape across the heads. Watch the meters and listen for the attack of the beat as you move the tape back and forth. Mark the exact center of the reproduce head with a grease pencil. Play the tape once more across the desired edit point to be sure you're in the correct spot. Place the edit mark in the center of the 45-degree angle and cut the tape with one smooth motion. On 2-inch machines, I use a steeper angle, usually 15 or 30 degrees. I'm going to add leader tape at this time so I can remove the unused edit pieces to another reel. When I'm done, I can place the pieces after the master take.
I'm going to pause that at that point. He goes on. He's got some more cuts to do, and you can watch the rest of it if you like. It is interesting, but it's a much more involved process. The editing of audio tape just not as convenient as digital editing that we're familiar with.